I hope I am audible to all of you.
Yes, sir.
Okay. So, uh, as ISC members mentioned that this technology day we celebrate uh, because on this particular day we have achieved milestone in nuclear capability. So in that series, I can say the next groundbreaking involvement of the India will be in the quantum technology. So the day we will be able to make a quantum computers. So that day will not be less than the Pokhran test. So this is our equivalent now capacity to revolutionize the country economy, country status in every field, not including the health, not including only education, but whatever field you can imagine, every field going to see a revolutionary change. Okay, so when Dhaneshwari told me that he the talk on the basic on the keep in mind that the technology is covered, I thought it's better to talk about quantum computing. We are also working on this quantum computing, and I want our students, okay, who are present in this class, in this webinar, so get inspiration. Okay, look in this field thoroughly, and this is a great opportunity for everyone. In the next coming 10 years, it is a time for the artificial intelligence as well as the quantum computing. So if you all can jump into this field, this will contribute not only for the personal growth but for the country's growth as well. So maybe I can share my slides and then we will keep talking about this. My slides are visible.
Yes, sir.
Okay. So the topic that I mentioned that we will be trying to look the future. Okay, this is going to be not change, as the quantum computing is going to evolve in not only in our country but the worldwide. So my name, as mentioned by Dr. Janeshwari Subham Kumar, and I'm working as a scientist in Entrepreneurship Accelerator Center. So just a minute. Yeah. Okay. So I have divided my talk in certain sections. So I will little bit talk about prospect. Okay, how the what kind of background led to the development of quantum computer, and then we will discuss about the difference between the classical computer and the quantum computers. So here I will discuss mostly quantum bits and the classical bits, and then once we enter in the quantum bits, we will talk about two very important major concept in the quantum mechanics. So one is called quantum superposition, and second is called the quantum entanglement, which are the basics of the quantum computing. Then how the quantum computer works? It is same like similar to concept like classical. So for example, in the classical quantum computers, we deal with the gates. Here also, we will be having a gates, and what kind of gates we have, we will discuss. So we will talk about one qubit, two qubits, or multiple qubits. And then in the fifth section, this is the where I am working. Okay, so I will discuss about my work. Okay, how we are actually planning to construct or build this quantum computer using the planar planning trap. And then there are huge possibilities that can be realized using the quantum computer. So I will talk only few which are of my interest. And if time permits, then also I will discuss what we are doing at now IAVC with planning tracks. So if you go back to the history, so I have just shown here the first classical computer. Now, that was known as ENIAC. Okay, so ENIAC stands for the Electronic Numeric Integrator in Computers. Okay, so this machine was based upon the vacuum tubes, and you can see that this was covering entire room. Okay, and the memory or the functioning of this computer was not more than not just 200 or 50 or not 500 MB. You can imagine the kind of chip you can carry in your mobile. Okay, that is much more capacity than having this computer at that time. So this was based upon the vacuum tubes. So next changes in the classical computer was came when transistors were made. Okay, in 1947, and that actually made the revolution in the classical computers. And now you can see that the size of this computer is drastically gone down, and this size is governed by very famous Moore's law. Okay, and this says that every year, okay, the size of the chips will going to reduce twice. But now you can see that the transistors we have one source and one drain and one gate. So this is talking about the size is reducing every year. It is reducing half every year. And now we have come to the limits. Okay, so we are already around 20 to 10 to 20 nanometer.
Sir, your slides are not changing. Yeah, now it is fine. Yeah.
That's fine, but if I still put in the
Presentation mode.
I got it. Discussing, so we will discuss one by one. So I already talked about it, so just keep this slide. I think better that we can again see. Can you see this picture? The room with the mouse and wires.
Yes, yeah.
And so this was classical computers. This was ENIAC. Okay, and you can see that this was made with the vacuum tubes. Okay, so vacuum tubes are very relevant. And this room, wide room, okay, around having one computer on it, which is just having same capacity like simple microchips. So the major change occurs when we got the transistors. Okay, so this transistors was first developed in 1947, and after that the size of the transistor started changing regularly, and this was governed by the Moore's law. Okay, and this is that the size will be half every year. Okay. We have reached the ultimate limit, and if you go further down, then what will happen that they will go into tunnel. So that case, the quantum tunneling is going to take place, and this will going to cause the electron to tunnel from the source to the drain, and there this MOSFET will not work. That is the ultimate limit. Okay, so we are reaching to this limit, and after a few years, the size of the computer will not going to decrease, which is based upon the transistors. Okay, semiconductor transistors. Because in this case, we are already reaching the 10 nanometers. I can now recommend students or anybody. You can interrupt in between and you can ask the questions for this. You should not wait for the last slide. Okay, otherwise you will forget. So, realized by the Feynman that changing for the quantum the transistors not going to help us to increase the quantum calculations, okay, classical calculations or similar computers. And I can say the person about the quantum computer. He mentioned that it's very important line, very famous, is at the bottom. So when you put atomic level, okay, the system is not governed by the classical rules. There the system is governed by the quantum rules. Okay. And he mentioned that we can harness the quantum property of the atoms or any subatomic system, okay, to do the calculations. So he, in that concept of life, he mentioned that there is plenty of root at the bottom, and we should look, okay, how we can harness the quantum property of atom, and that actually, so the seed for the quantum computations. In fact, he invited many scientists at that time who can come and make smaller and smaller machines. Okay. So we don't go too much into that experiment, but you must understand that Richard Feynman was the first person who gave the ideas of the quantum computation. And of course, when the quantum mechanics was developing, so in the 20th century, okay, you know that these are the person who played an important role in the quantum mechanics. One was against the quantum mechanics, but why he was against the quantum mechanics? Okay, to prove the probabilistic nature of quantum mechanics was not true, he developed some concept, okay, which helped later on to develop the quantum mechanics of the quantum computer. For example, he gave the concept of the entanglement, okay, and a very important paradox called EPR paradox, okay. So he developed this EPR paradox to prove that the probabilistic nature of quantum mechanics is not true. And of course, just 2 years back, Nobel Prize was given, okay, on proving that Albert Einstein's concept was not correct. But we should not criticize Albert Einstein, because to prove that, in order to prove that the probabilistic is not true, he gave the very important concept called EPR. Different from the classical world, okay. So here we assume that particle, okay, is going to have a associated wave subset. Okay. So particle is not only going to behave like a particle, it is going to behave like a wave also, and this wave has associated probability wave function that is called psi x, okay, and we study in the quantum mechanics, in the basic quantum mechanics, how these wave functions are useful to understand the quantum mechanical system. So in the quantum world, we think about that energy levels are not continuous, but they actually to understand very important, now very fascinating phenomena called superfluidity, okay, or Bose-Einstein measurement system. Led to the development of the QED, quantum electro analysis, okay, which is giving the very now very high precision. Quantum mechanics is a tool to understand the behavior of the subatomic particles. You can call it a tools, okay, but it is actually of the experimental results. Now, if you look at the tools which are getting useful to make a quantum computer, okay, that rule, one important rule is that you have to say that the particle is behaving like a wave. It's not just a wave packet, but it's actually made of a large number of different waves of different wavelength. Okay. So you can say that the wave function is nothing but a superposition of many such waves. If you take a spin, spin has only two such states, okay? So upspin and downspin. That is some superposition of these two states. So this property, the superposition property of a wave is actually useful to make the qubit, quantum bits. Okay. So here you will not go for more than two states, so only two states. In the classical word, we also talk about the bits. Okay, bits means two states. Okay. So for example, of course, if you are not doing any measurement, so you the momentum externally any of the quantum states, but you not doing measurement, then this is going to persist. So these properties are useful for the quantum computer. So I can show you a simple video that actually having advantage of classical computer. So if you want to go to, okay, let us say from one from okay to this given point, then in the classical world this wall, okay, is going to explore all possible paths, okay, and finally it will reach to the exit. But if the particle is a quantum particle, then it will explore all the possible paths. Okay, so calculations. I could show you one more video. Okay. Just it's the actual phenomena that is happening, that these particles are behaving like a wave. Okay. They're not a particle. Don't think they are particle. So you can think like a water entering into a tunnel, okay, which has many tunnels. Okay. It's not like that the first water will go to one path and return back, and again go to the second path and return back. This water will going to flow, okay, in every tunnel at the same time. So it is going to explore all the possible paths at the same time, and you can see that by exploring the all possible paths, okay, it is going to find the one path, okay, which led to the exit. All right. Is it clear to everyone what I am trying to show here? advantage of quantum computing, okay, that ask a quantum computer to do some calculations, okay, so it will explore all possible results, okay, and simultaneously, and will give you the correct answer, okay, at the end. This was, I can say, brief picture where you are able to see that how the quantum, in the quantum system, all the possible outcomes are accessed at the same time. Okay? And of course, at the present time, there are many players in the market. IBM is still leading, okay, and they are producing, okay, qubits more than 400. Remember that they mentioned that the qubits are more than 400 or 500 like the TV. Remember that unless you do not entangle the qubits, they are not going to be used for the quantum computing process. So you can predict 1,000 qubits, okay, but you are not going to entangle them. You are not going to solve the process. So if possible, IBM, they might be just able to entangle 10 to 20 qubits only, not more than that, although they prepared, they came up with the more than 400 qubits. Okay, anyway, this is a Canadian company, completely different aspects, coming up with a very they are the futures also. Almost they like quantum technology, and they are spending huge amount of money to build quantum that in India, if we are able to very ambitious project, and in this ambitious project, the idea is to demonstrate what people 50 to 50 and 50 to 1,000 qubits in complete area. This is the highly okay, how long we take to realize this magic figures. So this government national quantum mission is not targeting only with quantum computers, just physical quantum computers, that is not one of the category of quantum computing, but we are also government also talking about the quantum communication, quantum sensing, and quantum intelligence. So in all these four fields, okay, this money is distributed, and the people all over the country are participating in the national quantum missions. This magical future of the country. using the bits or trapped ion qubits, and so on. In the quantum communications, we have the possible fields, quantum material and voices, the other possible sections, quantum sensing and metrology, the other possible sections. So here, I mean, the future lies now for all the graduate students or master students like you. Okay, so you must do your study and focus on these fields that in the future will give you a contribution.
Not regarding this, but I have that question regarding that maze problem, that maze thing that you showed.
Yes.
In that case, what about the speed of the system? Will it take the same time in both the cases? Because it seemed as if in both the scenarios the time was same.
No. Well, in the slide it looks like same. Okay. But if you look in the classical case, the one particle is reaching to the one corner and return back. Okay. And then to the second. And I mean, you could explore all the possibility one by one. Okay. But if the system is quantum, so where it's again think like a water, okay, going into tunnel, right? So there are many tunnels interlinked, but only one tunnel is going outside. So this water well is entering inside the tunnel, so it is not going that it will explore the first tunnel, and let us say it is having an end, it will come back, explore the second tunnel, again come back, then third, fourth, like this way. So when you go and come back, it will consume time. So in the quantum computing, okay, all these possibilities are explored in the same time. You can say the system is going to sniff, okay, all possible paths in a single shot. Out of that, one path is correct.
Okay.
So in that sense, the quantum computing is definitely going to take less time, drastically less time in comparison to the classical computers. But of course, when you are, I mean, if you're going to use them for the classical world calculations, okay, they may not be very useful. I can talk later bit, okay, because they are going to have quantum errors, okay, and there it may not be much useful now to do a classical. For example, if you want to do some addition numbers, okay, so adding numbers, okay, is not useful to the quantum computer than doing in the classical computers, because not only the speed is the matter, its outcome also matters. In the quantum computer, you will not going to get the 100% data transfers. You will only get the possibility of the good answer, maybe 90%. But depending upon the quantum error correction, it may be 60% answer. You have to live with that. If you have to live with that, if you getting the 70% one possibility, then you have to imagine this is a correct answer. Okay. But if your quantum error correction is not good, then this 70% may also be wrong. So regarding to your question, the answer is yes. The quantum computer will take less time.
All right.
So I mean here, since I am talking only about the quantum computer part, okay, so not on the communication or the methodology. So here you can think there are many possible ways, okay, to realize the quantum computers. So one of them is manipulating a single ions, okay, or single atoms or single photons. Okay, so accordingly you have different types of system like ion trap. So I will be talking about ion trap only in my talks, okay, but there can be atoms in optical trap, so where you can trap neutral atoms. Cavity QED, where you can use the photons for the quantum, realize the quantum computers. Then of course you have supercomputers. Semiconductors also are not a very potential candidate to win the quantum computers. Okay, and of course now you can also use the superfluid system also of the quantum computers. So here my talk will be not only in one section, that is called the ion trap, where we're going to use ions to make the quantum computers. So just a little bit idea. You all are very good in the, I think, using the computing. So just